Imagine a world where all of Earth's roughly 1,500 potentially active volcanoes erupt simultaneously. While extremely unlikely, let's explore the hypothetical impacts of this catastrophic event, drawing from volcanology, geology, and related sciences. Currently, around 50 to 70 volcanoes erupt annually worldwide. This ongoing activity is part of Earth's natural volcanic processes, with eruptions occurring at various locations around the globe. Recent examples of active volcanoes include Kilauea in Hawaii and Etna in Italy, both of which have shown ongoing eruptive activity in recent years. The 2023-2024 eruption of Tonga's Hunga Tonga Hunga Ha'apai volcano demonstrated the power of individual volcanic events, injecting large amounts of water vapor into the atmosphere and temporarily affecting global temperatures. Importantly, there is no evidence to suggest that volcanic activity is coordinated or triggered by a global mechanism. Each eruption is driven by local geological processes. Volcanoes come in different types, each with unique characteristics and eruption styles. Stratovolcanoes, also called composite volcanoes, have steep, conical shapes built from layers of lava and ash. They produce explosive eruptions due to thick, viscous lava that traps gases, leading to violent blasts. Mount Fuji in Japan is a classic example. Shield volcanoes are characterized by their broad, gently sloping profiles, resembling a warrior's shield. They erupt fluid, basaltic lava that flows easily over long distances, creating extensive lava fields. Mauna Loa in Hawaii is the largest example. Supervolcanoes contain enormous underground magma chambers that can lead to catastrophic eruptions. When they erupt, the ground above collapses, forming a large caldera. Yellowstone in the United States is a well-known supervolcano with the potential for global impacts. Regardless of type, all volcanic eruptions are fundamentally driven by magma rising from deep within the Earth. This magma originates from the mantle or forms when tectonic plates melt, propelled upward by heat and pressure differences. The scale of a simultaneous global eruption would be unprecedented, involving all approximately 1,500 volcanoes on Earth erupting at once. Such an event would involve a range of eruption styles. Explosive eruptions produce violent blasts with ash and pyroclastic flows. Effusive eruptions release gentle streams of lava. Phreatomagmatic eruptions occur when magma meets water, creating steam explosions. This catastrophic event would release immense quantities of lava, ash, gases such as carbon dioxide, sulfur dioxide, and water vapor, as well as deadly pyroclastic flows. The scale would dwarf any historical event, with approximately 1,500 volcanoes erupting simultaneously. Total magma volume could reach about 10 to the power of 18 cubic meters, lasting months to years with varying intensities on the volcanic explosivity index scale from 1 to 8. Overall, the scale of a simultaneous global eruption would be catastrophic, releasing materials and energy on a planetary level that would dwarf all known volcanic events combined. The atmospheric injection of massive amounts of aerosols from simultaneous volcanic eruptions would trigger what scientists call a volcanic winter, where particles block sunlight and cause global temperatures to plummet. In this scenario, volcanoes worldwide would release between 10 trillion and 100 trillion tons of fine particles and gases into the atmosphere. These aerosols form a thick haze that reflects and absorbs incoming sunlight. This aerosol layer acts like a global parasol, preventing a significant portion of sunlight from reaching Earth's surface. The result would be a dramatic cooling effect, with global temperatures potentially dropping by 5 to 10 degrees Celsius. This cooling effect could persist for several years as the aerosols slowly settle out of the atmosphere. The scale of a simultaneous global eruption would far exceed historical events, such as the 1815 eruption of Mount Tambora in Indonesia. Acid rain forms when sulfur dioxide released by erupting volcanoes reacts with atmospheric water vapor, creating sulfuric acid that falls as precipitation. This acid rain severely damages agriculture by harming plant tissues, depleting soil nutrients, and disrupting the delicate balance of soil microorganisms essential for healthy crop growth. The result is widespread crop failure that could trigger famine on a global scale, threatening food security for billions of people. The eruption would also release a massive amount of CO2, ranging from 100 to 500 gigatons. This enormous release would potentially exacerbate climate change, raising global temperatures by 1 to 2 degrees Celsius in the long term. This creates a complex interplay between short-term cooling effects from volcanic aerosols and long-term warming from the CO2 emissions. While volcanic winter brings immediate cooling, the greenhouse gas buildup leads to sustained temperature increases. A simultaneous eruption of all volcanoes would trigger widespread seismic activity across the planet. The intense volcanic activity would cause frequent earthquakes as magma movement destabilizes tectonic plates. These earthquakes could generate massive tsunamis, especially along coastal regions near subduction zones. Ground shaking would also trigger landslides, particularly in mountainous areas with unstable volcanic slopes. Together, these secondary disasters would amplify the volcanic destruction, creating widespread chaos and loss of life. The duration and magma volume of a simultaneous global eruption would be unprecedented in Earth's history. The eruptions could span months to years, depending on the volcanic activity in different regions. The intensity would vary across the volcanic explosivity index scale from 1 to 8, with different volcanoes showing different levels of activity. The total magma volume would reach around 10 to the power of 18 cubic meters, an unprecedented amount that could potentially reshape entire continents. The Toba supereruption occurred approximately 75,000 years ago in what is now Indonesia. This massive volcanic event ejected about 2,800 cubic kilometers of material, making it one of the largest eruptions in Earth's history. The eruption created a decade-long volcanic winter, as massive amounts of ash and sulfur dioxide blocked sunlight and cooled the planet's surface. This event provides insight into potential demographic collapse from a global volcanic catastrophe. The human population bottlenecked to an estimated 10,000 individuals, nearly causing extinction. The 1783-1784 Laki fissure eruption in Iceland serves as a powerful example of how even regional volcanic activity can have devastating global consequences. Located in southern Iceland, the Laki volcanic fissure erupted in 1783, creating a 27-kilometer-long crack in the Earth's surface. Over 8 months, it released approximately 120 million tons of lava and toxic gases, including sulfur dioxide and fluorine compounds that poisoned the air and water. The eruption killed an estimated 20 to 25% of Iceland's population through lava flows, poisonous gases, and subsequent famine. The massive release of sulfur dioxide created acid fog that spread across Europe. This led to unusually harsh winters and crop failures throughout Europe, contributing to widespread famine and economic hardship in the following years. Although not a global event, the Laki eruption demonstrates how regional volcanic activity can cause far-reaching environmental and societal impacts, affecting weather patterns and agriculture thousands of kilometers away. This historical event underscores the importance of understanding volcanic risks and preparing for their potential widespread effects. Volcanologists and geologists consider the simultaneous eruption of all Earth's volcanoes extremely unlikely. According to USGS estimates, the annual probability is less than 0.001%. Despite this low probability, experts use this hypothetical scenario as a valuable tool for risk assessment. It helps us understand how Earth's systems are deeply interconnected. As volcanologist Terry Plank from Columbia University noted, it's a thought experiment showing Earth's fragility. Geophysicist Clive Oppenheimer emphasizes that preparedness through early warning systems could limit fatalities to millions rather than billions. Key statistics show that while volcanic activity is natural and ongoing, with annual deaths averaging 1,000 to 2,000 and eruptions releasing about 0.2 gigatons of CO2 yearly compared to humanity's 40 gigatons, understanding these systems helps build resilience. The educational takeaway is clear. Rather than fear, we should focus on mitigation strategies and preparedness to protect our planet and its people. Rising global temperatures from climate change are creating new risks for volcanic activity. As the planet warms, glaciers melt at an accelerated rate, reducing the weight pressing down on the Earth's crust. This melting decreases pressure on magma chambers beneath the surface, making it easier for molten rock to rise and potentially trigger eruptions. The effect is particularly pronounced in polar regions like Iceland, where massive ice sheets cover active volcanoes. As these glaciers retreat, volcanic unrest could become more frequent. Scientists, including those from a 2023 Nature study, warn that this could lead to more volcanic eruptions worldwide, highlighting the interconnected relationship between climate systems and geological activity. Looking ahead, advanced technologies are transforming our ability to monitor and predict volcanic activity, helping us prepare for potential eruptions. Advanced technologies like deep Earth imaging offer the potential to better predict volcanic unrest and mitigate risks. AI-enhanced models now predict eruptions with 70 to 80% accuracy up to weeks in advance. These AI-enhanced models now predict eruptions with 70 to 80% accuracy up to weeks in advance, giving communities valuable time to prepare. While simultaneous eruption of all volcanoes is highly improbable, a cascade of eruptions triggered by seismic chains could amplify impacts, creating regional or hemispheric disturbances. One eruption can generate seismic waves that destabilize nearby volcanoes, setting off a chain reaction that spreads across regions. This cascading effect could cause widespread regional disturbances, though not global catastrophe. The ash fallout from a simultaneous global eruption would have devastating effects on agriculture worldwide. Volcanic ash clouds would block sunlight, preventing photosynthesis in plants and drastically reducing crop growth. According to scientific estimates, global crop yields could decrease by 50 to 80%, threatening food supplies for billions. This massive reduction in food production would lead to widespread famine, potentially causing societal collapse as populations struggle to survive. Despite the catastrophic potential of a global volcanic eruption, historical examples show that both ecosystems and human societies can demonstrate remarkable resilience and adaptation. After major volcanic events, life finds ways to recover and rebuild. Take the Toba supereruption from about 75,000 years ago. This massive event nearly caused human extinction, with populations bottlenecked to just a few thousand individuals. Yet, ecosystems eventually regenerated and human societies recovered. This demonstrates nature's incredible capacity for regeneration. Even after devastating volcanic winters that last for years, plant and animal life can rebound as climates stabilize. Human societies have shown similar resilience. Through innovation, migration, and community support, people have adapted to volcanic disasters throughout history, developing better warning systems and rebuilding stronger communities. This resilience reminds us that while volcanic events can be destructive, they don't have to define our future. With preparation and adaptation, we can mitigate their impacts and continue to thrive. Mitigation strategies focus on reducing the impact of volcanic eruptions through preparedness measures. Robust early warning systems use seismic sensors, gas monitors, and satellite imaging to detect volcanic unrest before eruptions. These technologies provide crucial time for evacuation and preparation. Such systems can significantly limit fatalities by enabling timely evacuations and emergency responses, turning potential catastrophes into manageable events. Drawing lessons from past disasters, like Pompeii, highlights the importance of timely evacuation. In 79 AD, Mount Vesuvius erupted without warning, burying the city under ash and killing over 2,000 people. Modern early warning systems prevent such tragedies by providing advance notice, allowing communities to evacuate safely and save lives. Investing in early warning systems is essential for volcanic risk management, combining technology with preparedness to protect populations worldwide. Volcanoes contribute significantly less carbon dioxide to the atmosphere compared to human activities. Annual volcanic emissions are about 0.2 gigatons of CO2, while human activities release around 40 gigatons each year. However, in a hypothetical global volcanic event, this could change dramatically. If all volcanoes erupted simultaneously, the massive release of gases could double atmospheric CO2 levels in just a matter of weeks. leading to rapid and drastic climate changes. The UN's Volcanic Risk Framework emphasizes the need for proactive mitigation strategies to reduce the impact of volcanic hazards. This framework becomes even more critical in light of potential climate-driven increases in volcanic activity. This hypothetical scenario underscores the interconnectedness of Earth's systems. The geosphere includes Earth's solid parts, the atmosphere is the air around us, and the biosphere encompasses all life. These systems are deeply interconnected, with constant interactions between them. A global volcanic event would originate in the geosphere, but it would create cascading effects across all these systems. By studying past eruptions and developing advanced monitoring and prediction technologies, we can better prepare for future volcanic hazards and build a more resilient future. Historical eruptions like the massive Toba event 75,000 years ago and the Laki Fissure eruption in 1783 provide crucial lessons about volcanic impacts and recovery. Modern technologies enhance our ability to monitor volcanic activity. Satellites track ground deformation, seismographs detect underground movements, and artificial intelligence improves eruption predictions with up to 80% accuracy. Building resilience involves early warning systems that alert communities, comprehensive evacuation plans, and infrastructure designed to withstand volcanic hazards. These measures can significantly reduce risks and save lives. Through continued research and international cooperation, humanity can learn from volcanic history to create safer communities and adapt to Earth's dynamic geology. While the simultaneous eruption of all volcanoes on Earth is highly improbable, this thought experiment serves as a powerful reminder of the immense geological forces that continually shape our planet. It underscores the importance of understanding natural hazards and developing strategies to mitigate their impacts on human societies. By studying volcanic activity and preparing for potential disasters, we honor the power of Earth while safeguarding our future.